Yeah, so we can go ahead with the next talk. We are happy to have Raphae Ducatez, who will be speaking on forward-backward random process for the spectrum of the 1D Anderson model. Raphael, please.
So thanks you very much. I'm very happy to be here to present this work. So yeah, please free to ask any question during the talk. I would not mind. So here's a question actually I will talk about for 20 minutes. So consider this just simple 3 diagonal matrices. So with the Laplacian, so just the one outside of the solution. And for the entry, we choose the entry as independent random variables. So here's your matrices. You will choose n quite large. And the question is, what does the eigenvector of this big matrix looks like? So some motivation for this question. So it goes back to in the 50s from a physicist called Anderson, which actually won a Nobel Prize for his works on condensed. And in the end of the 50s, he gave a very interesting prediction, which I tried to state in this sentence, that for a long time behavior in disordered media, no dissipation can take place under certain assumption, of course. So what he had in mind, so you can think of a piece of metal, so which modelized by a lattice, and an electrons in the lattice that evolved in the lattice. And the important word here is disordered. So disorder means that the system is far from being homogeneous, so there will be plenty of irregularity or impurity, etc. So to modelize it, we will choose a potential on this lattice, which is random. And to see the evolution of the electrons, we solve the Schrödinger equation with some operator which is minus Laplacian plus v. So the matrix which I just saw in the first slide was just the. Yeah,
is it so? This on our screen.
It's Raphael.
Raphael, could you check on the bottom right corner? We see some things which start with good morning. Okay, thank you.
Okay, yes, okay, sorry. Okay, okay. Yeah, okay, well, so let me carry on. So yes, so I said just that the matrix story is just a one-dimensional case of this model. And well, and what does no diffusion can take place? Well, you have the Schrödinger equation in just a linear equation. So, well, if you want to know the dynamics, it's just enough to diagonal this operator. So, if in the case with no potential at all, so with no disorder, we all know what the eigenvector are. It's just the plane wave. So that's it. And it's a curious phenomenon, so which was predicted by Anderson, is that if the disorder becomes large enough, the eigenvector looks like these kind of things, which stays kind of localized in space. So actually, you can take an infinite box if you want to. Still, the eigenvector would just be like localized on a bounded domain, and that's what's called localization. And it's been a long, it's been studied both in physics and mathematically for a long time. So let me make a brief historic of this. So as I said, it was just proposed by the physicists in the beginning of the 60s. And then from a mathematical point of view, if you have to remember a few names, let's state Froelich and Spencer, and then Eisenman and Molchanov, that proves the localization phenomena in any dimension for the strong disorder cases. But it's still like an ongoing process research now, and which we are kind of very far from understanding this phenomena well enough. So let me go back to the one-dimension case. So the real result I will propose to you is just a way to construct the eigenvector. So well, actually, the starting point is extremely easy. So you have your matrix, your three-diagonal matrix, and you write what being an eigenvector of H means. So with an eigenvalue lambda is just satisfied for A and these simple equations that you can rewrite as second order recursive equations. So as UN plus 1 based on UN and UN minus 1, which can be written as a matrix, just by 2 by 2 matrix. That case. And well, so you can express any point of the vector as a product of these 2 by 2 matrix. So I just call this matrix T lambda of VK. And from and well, if you just look at it, you say, okay, that's quite nice. Actually, all the VK are independent. So we just have a product of independent matrices that's going on. That's it. Actually, it's not that easy because the lambda here, so it's and the eigenvalue of H is also random. So lambda here depends on all the VK of the matrix. But okay, well, we can, let's say that for, okay, just that we want to forget about this difficulty and imagine that lambda is fixed. So this gives rise to, like, I would say, like a simple process, which is the forward product of random matrices. So you fix the first vector and you make this product with IID potential and fixed lambda. Well, I call it forward process because, well, we can do it exactly the other way around. I mean, you have written here the equation with UN plus 1, but you can just as easily exchange UN minus 1 here and put the UN minus N plus 1 here. So just if you exchange these two, you go, you express the other way. So what appears is also a product of matrices, but you start from the end, so with UN and U0, and you make a product of random matrices going backward. And I say that there is the free natural process. Of course, the one we're interested in is the eigenvector of H. Yeah. So kind of natural question is, well, are these processes really that different, or are they like linked one to another? So actually, yeah, the behavior coming from the different process, like kind of very different. So just as an example, which okay, I've drawn here, so that the forward process for different value of V and but for value of lambda. But the behavior for the forward process is, okay, if I drew the logarithmic of this, it's like a Brownian plus a drift. So a drift which is increasingly linearly and Brownian. So in a way, it's so this is for the forward process, and if you do the same for the backward process, well, you see the same behavior, but obviously in the other direction. And well, that's it. I mean, that's the two pictures are completely different, just completely the reverse of one thing. And if you draw the eigenvector, this the logarithmic of the vector, this is what you looks like. You can think of here is the point of localization. That means that most of the mass of the eigenvector is localized here, and in this part it is exponentially small, and in this part it is exponentially small. And well, and actually, what I will present to you is just that there exists a quite simple construction of this eigenvector using these two processes, so the forward product of random matrices and the backward product of matrices. So we follow just like the vector u and un plus 1. So you can just kind of think of them as a point in C, and we'll write it as a radius part and the phase path. The phase path can be interesting because, well, if you do the product, if you apply the matrix, well, we can forget about the R, since the phase do not depend on the norm. So I will use an abuse of notation that this is matrix, but it's not really matrix. Act on the phase and just gives the next phase. And then, well, I will denote P just the forward process of matrices and the backward process of matrices. And here X is, I keep track on all the phase, but you should think X as just an expression of the eigenvector. So I just, it's a bit more convenient to track just the phase. You can obviously recover the R when you know the phase and the other way around. So let's take the main equation. Is the following. So here we say that for any test function we have this equality. So an equality here and for any test function should be understood as follows: that the law on the left hand side, so this is like, should think of it as a random things, is exactly the same as the law described here. So here is a random variable, and here is also a random variable, and a way to draw the lambda and x. So what is the left hand side? The left hand side here is draw the random potential, so all the v1s are okay, and then the 1 over n over sum is draws an eigenvalue and an eigenvector. So x is the eigenvector. So this is like, I'll say that the completely natural way to say this is a random eigenvector. And this other process goes as follows. So choose, fix a lambda in R first, then draw a point K between 1 and n and draw it uniformly. So this is just 1 over n sum K. So this, and then when you have this K draw, it will represent a cut. So you cut your segment 1n into 2 parts. So 1K and K plus 1n. And in the left-hand side, you do the forward process. And in the right-hand side, you do the backward process. And you make sure that these two processes actually are coincide in K, so that's not well, that's the value of the phi k are the same, and that's it. And this constructs you the way to construct x and this lambda. And there is a small.
Sorry.
Yes.
Where does the sine square phi k come from?
Well, it came from some change of variable. So. Okay, well, I will not present exactly it came from some way. The idea proves kind of change of variable, and if you do the derivative of this kind of matrix, of the action of phi, it gives you the phi squared.
Okay, no worries. If it's too complicated, let's.
No. Well, I mean, you can write the 2x2 matrix, the application from phi k to phi k plus 1 and derivative it with lambda, and what pop out is kind of sinus of phi. So yeah, so actually the idea of the proof of this equation is really simple change of variable. It's not what you want to is fix lambda. okay, express, okay. You have the v and the lambda, and you would like to make a change in variable between one v and one lambda. It's not that the good way to do it is to make a change of variable between one, which is lambda, and one random v. That's kind of the way what this equations is about. So I will just now show you some application of this equation. So the first one is for the density of eigenvalue. So I write ny is the expected number of eigenvalue of smaller than lambda. So here is the density of eigenvalue. So it is a probability that for fixed lambda, this lambda is an eigenvalue of the matrix. And well, if you just use the previous formula, you can define rho of phi, which is the probability of the phi k, of the phase after k iteration. So you make a process ring forward, and you have a random phi k after k iterations. And you can do also the same in the other directions. You do the same in the backwards. And the probability actually that lambda is an eigenvalue is exactly the probability that the two processes coincide exactly. And so it's expressed as this equation. And because the cut k is uniform between 1 and n, while you have to sum to have this expression for the density of eigenvalue. And if you now can think of, well, you can take your matrix and do it like send n to infinity. Well, this will converge to a limit, and because, well, the law of the phase actually converge also as an invariant measure, and so as the backward process. So we get this simple formula, which was actually well known from and can be found for this very classical book of the subject by Cameron. So another application, actually, I think that's the most interesting one, is the connection with some limit theorems for products of random matrices. So actually, product of 2x2 matrices has been well-studied subject, and let me show you some of nice results. So I'm interested in the logarithmic of the norm of this issue. So MIID random matrix, and we do the product and we apply it on some x. So just this is a log of a product. So let me write it as a sum. So I just smuggle it as this norm and put it outside. And I will do it n times. So I just get sum of log with m then is independent matrices. And here I have a random norm 1 vector. And you can naively say that, well, okay, well, all these are kind of should behave like IID random variable. It's not quite exact, of course, because this vector y depends on all the past mi, but it happens that there is some mixing properties on the y. So after a few steps, actually, the y completely forgot what happens a long time before. So for k and k prime far away from each other, they can be almost considered as independent. And the heuristic is kind of true to consider them as an IID random variable, because we get most of the most interesting results from IID random variable, meaning that there is the law of large number. So if you divide the sum by n, then with probability 1, these things will converge to some explicit constant, which actually is called the Lapianov exponent. exponent. Well, this is the first step. Actually, you can go even further. So if you remove this drift and then divide it by 1 over square root n, you get the central limit theorem. That means that this is a random variable, of course, and with the correct rescaling, it will converge to the Gaussian variable. And well, you can also have the continuous thing of the down-curve theorem, which is it's like direct extension of the central limit theorem, which is that we have a convergence to a Brownian motion, and also some large deviation theory means that the probability that this matrix go far away from the drift it should go is actually exponentially small. And all these results actually are, we say, well known, and this is a good reference. Okay. It's in French, but this is the one I used. So maybe I can give you a brief idea of how one can prove this theorem. The nice idea is to introduce this operator. So it's the application of f. So this is you kind of make an you take a mean of this function f with the random vector of norm 1, and you add this mass here depending on alpha and of log n. Well, if you forget about the f, you should think of it as the Laplace transform of the random variable. And actually, the Laplace transform is the most, I would say, the most useful tools for studying this kind of random objects. So and the main property of this A of alpha actually is that it has a unique eigenvalue well, and there are of course some nice property of M. And we call it this largest eigenvalue J of alpha. And then if you iterate many times A of alpha, well, because it has a unique largest eigenvalue, A of alpha will converge to G of alpha power n. So you can forget all the other space because it will decay exponentially fast compared to G of alpha. And this G of alpha, which is completely dominated by G of alpha power n. And if you ask for the probability of this, actually by Markov property, you can bound it by these things, and this actually is exactly this operator. So in a way, the logarithmic of this norm actually is just kind of an iterative of this operator, and because it has largest eigenvalue, it just makes the G of alpha appears. So here's the proof for the large deviation estimate. And for the central limit theorem, it's basically the same, but with a choice of alpha, which is IS square root of n. And if you do the same, actually, well, what we do, you also do a linear expansion of G alpha. And this is a procedure it goes. And it should converge to the Fourier transform of the Gaussian, which is also the Gaussian. So this is basically the idea. And the good thing is, well, this all, okay, well, that's all, as I say, was well known for product of random matrices. But then we can apply it for the eigenvector. So as I said, the law of the eigenvector is as follows: you draw a random cut between the system. So here the cut, you can guess it is basically here. And in the left-hand side, you have a drift plus the Brownian motions, and the right-hand side, the drift of Brownian motions. So the drift is, okay, this is actually another proof for localization. So we have the vector is localized around the cut, and the left-hand side, we have the drift, exponential decay, and we know the fluctuation around this exponential decay on the left-hand side and the right-hand side. And okay, well, that was the last maybe short application we just talked about. Okay, well, this actually was a previous work before our work, and it was the main inspiration for the formulas that I presented is that if you change the potentials, then it's I call critical because the potential becomes weaker. Here, the convergence to the Brownian motion and the things became exact. So actually, with the correct rescaling, so it was a work by Rifkin and Virag, with the correct rescaling, the Laplacian plus V actually becomes like Laplacian plus a white noise, and studying this gives exactly exponential of Brownian plus drift. And well, I think I will stop here. So thank you. Thanks a lot for your attention.
Thanks a lot. Please, questions or comments? I have a question. If you go back to the slide where you have this plot for log, right? So here, you know the behavior on the left, you know the behavior on the right, but I haven't. Maybe that's a stupid question. I haven't quite understood the behavior for the whole thing. Where on the left there would be drift in one direction, and on the right the drift on the other direction. Is there the law for the?
So you should think of the constructor. You should think of the constructor, the eigenvector, as gluing the two processes together. Sorry. I don't hear you anymore.
Yeah, sorry. Yeah, I kind of with muting and unmuting, I kind of got confused. So, right, you can I write one formula for the law which applies both on the left and on the right, and which would restrict to those Brownian motions with a drift on the left and on the right, but and at which point and how do I glue that I don't quite understand.
The point is random. That's
okay, but can one write some kind of law, or I mean, like similar to the law for the log that you have now, right? You have a law which says it's a drift plus the Brownian motion. Now maybe you need this random point in it or something, but can you write a combined law for the whole range?
So okay, well, maybe you can just go to the critical model, because there the thing is exactly exact, which is okay. It's basically kind of the same. So you have how write it? Yes, you have this function S, which is exponential of Brownian motion minus the absolute value of x. So absolute value of x means that there is a drift on the right-hand side and the drift on the left-hand side. And actually, the rule is that there is a minus u, which is random. So the center where there is a drift on the left-hand side and drift on the right-hand side is random and uniformly into in the domain.
Okay, and that's the answer. Wow. Sorry, and that will be the answer in your case as well. So this point, this random point, it will be it will be evenly distributed over the
yes
interval?
Well, okay, it's not exactly okay, well, okay, it's for len, okay, it's not exactly uniformly distributed, but for n large, the law of the cut will converge to the uniform distribution.
Okay, Thank you. So again, sorry for taking all the time with my questions, but maybe the audience should be more active on the next talks. So thanks again, Raphael.